Welcome to the Chill Scientist. Let's jump right into today's topic, Saturn. For as long as humans have looked up at the night sky, Saturn has been one of the most captivating wanderers. To the unaided eye, it appears as a steady point of golden light, slower than Jupiter and far less dazzling than Venus, but still noticeable among the stars. Ancient astronomers in Mesopotamia carefully tracked Saturn's movements, noting that it took nearly 30 years to make one full journey across the sky. They gave it special significance, associating it with long cycles of time, patience, and endurance. For the Romans, Saturn was identified with the god of agriculture and time itself, Saturnus, whose yearly festival, Saturnalia, became one of the most celebrated holidays of the ancient world. The Greeks tied the planet to Cronus, the Titan father of Zeus, ruler of the Golden Age, and a figure of both abundance and inevitability. The slow passage of Saturn through the constellations seemed to embody the relentless march of time, making it not just another planet to watch, but a cosmic marker of fate and cycles. This symbolism lasted for centuries and even made its way into medieval astrology, where Saturn was often considered a planet of seriousness, discipline, and limits. To early sky watchers, its golden hue and stately pace set it apart. Despite its importance, for thousands of years, Saturn remained a mystery. No one could see its true nature until the invention of the telescope in the early 1600s. When Galileo Galilei turned his small refracting telescope toward it in 1610, he saw something that left him puzzled. The planet appeared to have ears, strange extensions on either side, giving it a triple-bodied look. Galileo sketched what he saw, but admitted he did not understand it. His telescope was too crude to reveal the truth, but he knew Saturn was unlike any other object in the heavens. It was Christian Huygens, a Dutch scientist, who solved the puzzle in 1655. Using a more powerful telescope of his own design, he realized that Saturn was encircled by a thin, flat ring. He also discovered Titan, Saturn's largest moon, in the same year, cementing 1655 as one of the great milestones in planetary science. Giovanni Cassini, an Italian-French astronomer, added more detail in the late 1600s, showing that the ring was actually made of multiple sections, separated by a dark gap, now called the Cassini division. Cassini also discovered 4 more moons: Iapetus, Rhea, Tethys, and Dione. By the end of the 17th century, Saturn had gone from a golden dot in the sky to a planet with a system of rings and moons, already hinting at its complexity. For most of history, telescopes provided only faint, blurry views of Saturn's beauty. The real breakthroughs came with space exploration. Pioneer 11 flew past in 1979, giving humanity its first close-up images. Voyager 1 and Voyager 2 followed in 1980 and 1981, revealing the intricate details of the rings, the odd features of moons like Iapetus and Mimas, and the strange atmospheric patterns circling the planet. Then, beginning in 2004, the Cassini spacecraft entered orbit around Saturn and stayed there for 13 years, sending back a torrent of discoveries. The geysers of Enceladus, the methane lakes of Titan, the fine structure of the rings, and even the giant hexagon-shaped jet stream at Saturn's North Pole. By the time Cassini ended its mission in 2017, by plunging into the planet's atmosphere, Saturn had gone from a mysterious dot in the night sky to one of the most studied and fascinating worlds in the solar system. What makes Saturn so compelling is not just one feature, but the combination of many: its immense size, its delicate rings, its family of over 140 moons, and its dynamic atmosphere, all combine to form a planetary system within a system. Each discovery about Saturn has raised new questions, reminding scientists that even after centuries of study, the planet has more secrets to reveal. The story of Saturn begins with curiosity and wonder. From the ancients who saw it as a symbol of time, to Galileo's confusion, to Cassini's final dive, Saturn has continually challenged human imagination and technology. It is a planet that sits far from Earth, about 1.4 billion kilometers, or 870 million miles, away on average, and yet it feels strangely close, because we have seen its rings with our own eyes, landed a probe on Titan's surface, and watched geysers erupt from Enceladus. Saturn has gone from myth to science, but it has never lost its ability to inspire awe. When measuring Saturn against the other planets, its scale is immediately impressive. It is the second largest planet in the solar system, smaller only than Jupiter. At the equator, Saturn's diameter is about 120,500 kilometers, or 74,900 miles. That makes it about 9.5 times wider than Earth. If you were to line up Earths across Saturn's diameter, more than 9 would fit side by side. Its sheer volume is even more striking. Over 760 Earths could fit inside Saturn. Yet despite this immensity, Saturn's mass is only about 95 times greater than Earth's, considerably less than one might expect for such a large planet. The reason is density. Saturn's average density is 0.69 grams per cubic centimeter, lower than that of water. This means that, hypothetically, if you had a cosmic-sized bathtub filled with water, Saturn would float. Of course, such a scenario is impossible, but the image drives home the unusual nature of Saturn's composition. Unlike Earth, which is built of rock, iron, and heavier elements, Saturn is composed mostly of the lightest gases in the universe, hydrogen and helium. This makes it a planet of bulk without weight, so to speak. Inside Saturn, scientists believe there is a layered structure. At the very center lies a dense core of rock and ice, estimated to be about 10 to 20 times the mass of Earth. Surrounding this core is a layer of metallic hydrogen, a bizarre state of matter that forms when hydrogen is compressed under extreme pressure, so tightly that its electrons move freely like those in a metal. This metallic hydrogen is thought to be responsible for Saturn's magnetic field, just as metallic hydrogen powers Jupiter's. Above the metallic layer lies a thick envelope of liquid hydrogen and helium, blending gradually into the gaseous atmosphere we see from space. The pressures and temperatures inside Saturn are almost beyond comprehension. At the core, scientists estimate that temperatures reach 11,700 degrees Celsius, or about 21,000 degrees Fahrenheit, hotter than the surface of the sun. The pressure there is millions of times greater than Earth's sea level pressure. Even hydrogen, the simplest and most abundant element, behaves in ways we can barely replicate in laboratories. Understanding Saturn's interior helps scientists learn not just about Saturn itself, but about the physics of matter under extreme conditions, which is also relevant to studying stars and exoplanets. Saturn's mass and composition also explain why it looks the way it does. Lacking a solid surface, Saturn is essentially a vast globe of gas, with clouds and winds dominating what we see. Unlike Earth or Mars, where landscapes and geology are shaped by solid crusts and volcanic activity, Saturn is sculpted by fluid motion and gravity. This is why its surface is so smooth, and its features appear as soft bands of color, rather than craters or mountains. Its place in the solar system also influences its properties. Saturn orbits the Sun at an average distance of about 1.4 billion kilometers, or 870 million miles. This makes it about 9.5 times farther from the Sun than Earth. Because of this distance, sunlight reaching Saturn is only about 1% as intense as what Earth receives. Despite this, Saturn still reflects enough sunlight to appear bright in Earth's night sky, largely because of its cloud tops and icy rings. One surprising aspect of Saturn is how much energy it emits. Saturn radiates about 2.5 times more energy than it receives from the Sun. This extra energy is thought to come from helium rain, droplets of helium separating from hydrogen in the planet's interior and sinking toward the core, releasing gravitational energy as heat. This slow process not only explains Saturn's warmth, but also hints at its internal evolution. Over billions of years, Saturn has been slowly sorting its elements, making its current state a window into both its past and its future. When comparing Saturn to Jupiter, the differences are instructive. Jupiter is more massive, with over 300 times Earth's mass, and its greater gravity compressed its gases into a denser planet. Saturn, though still huge, is puffier and less compact. This makes it more fragile in a sense. Its gravity is weaker at holding onto heavy materials, and its atmosphere is less tightly bound. These differences show how even two giant planets made mostly of hydrogen and helium can turn out quite differently depending on the details of their formation and evolution. Taken together, Saturn's size, density, and internal structure reveal a planet that is immense but delicate, massive but light. It is a world defined by gases and pressure, shaped not by rock and crust, but by forces deep in its core. Saturn challenges our Earth-centered perspective by showing what a planet can be when it forms far from the Sun, in a region rich with hydrogen and helium. Understanding these basics lays the foundation for exploring Saturn's atmosphere, rings, and moons, the features that make it one of the most fascinating worlds in the solar system. Saturn is a planet of extremes, and its basic motions, the length of its day and year, highlight just how different it is from Earth. Despite its enormous size, Saturn spins on its axis at remarkable speed. A full rotation takes only about 10 hours and 33 minutes, meaning one Saturnian day is less than half the length of an Earth day. For a planet over 120,000 kilometers, 74,900 miles, wide, this rapid rotation is astonishing. The speed at which different regions of the atmosphere rotate is not perfectly uniform, so measuring Saturn's exact day length is surprisingly difficult. Scientists have relied on the planet's radio emissions, magnetic field measurements, and atmospheric tracking to pin it down. But even now, the number has small uncertainties. This rapid spin has consequences. Saturn is not a perfect sphere, but an oblate spheroid, which means it bulges at the equator and flattens at the poles. The difference is striking. The equatorial diameter is about 120,500 kilometers, 74,900 miles, while the polar diameter is about 108,700 kilometers, 67,600 miles. That's more than a 10% difference, making Saturn the most flattened planet in the solar system. If you were to look at Saturn without its rings, you would still notice its squashed appearance compared to rounder worlds like Earth. This extreme flattening is a direct result of how fast Saturn spins, combined with its fluid gaseous composition. In contrast to its short day, Saturn's year is long. The planet takes about 29.5 Earth years to complete a single orbit around the Sun. That means if you were born on Saturn, you would wait nearly 3 decades before celebrating your first birthday. This long orbital period was known to ancient observers, who noticed Saturn's slow, steady movement through the zodiac compared to the faster planets like Mars or Venus. From Earth, Saturn appears to creep across the night sky, lingering in each constellation for over 2 years before moving on. Saturn's orbit places it at an average distance of 1.4 billion kilometers, 870 million miles, from the Sun, or about 9.5 astronomical units with 1 AU, being the distance from Earth to the Sun. Because of this great distance, Saturn receives only about 1% of the sunlight Earth does. Yet despite the weak sunlight, Saturn remains visible and even bright in the night sky, thanks in part to the reflectivity of its atmosphere and its rings, which act as giant mirrors scattering sunlight. The tilt of Saturn's axis adds another layer of complexity. Saturn is tilted about 26.7 degrees relative to its orbit, very close to Earth's tilt of 23.5 degrees. This tilt means Saturn experiences seasons, just like Earth, but on a much longer timescale. Each season lasts more than 7 Earth years. For example, when Cassini arrived at Saturn in 2004, the northern hemisphere was in winter. Over the course of its mission, which lasted until 2017, Saturn shifted from northern winter through spring and into summer, giving scientists a rare chance to watch seasonal changes unfold in real time. These seasonal shifts affect not only the atmosphere, but also the rings, which change their angle relative to the Sun and Earth, altering their brightness and appearance. Because Saturn's rotation is so fast and its year so long, the rhythms of life on Saturn would be unlike anything familiar on Earth. A day would whip by in less than half the time we are used to, while a year would stretch across nearly 3 decades. The flattening caused by rotation would make the horizon curve differently than on a spherical planet, and the long seasons would create extended periods of atmospheric change. For the moons orbiting Saturn, these factors also shape their conditions, with years of continuous sunlight or darkness at the poles, depending on the season. Understanding Saturn's day, year, and shape is not just a matter of trivia. These basic parameters influence nearly everything about the planet. The short day drives the strong jet streams and atmospheric banding that dominate its weather. The oblate shape alters its gravitational field, which in turn affects the orbits of its moons and the dynamics of its rings. The long year and tilted axis create extended seasonal cycles that affect temperatures, cloud patterns, and even the chemistry of the atmosphere. These fundamental characteristics are the foundation upon which Saturn's more complex phenomena rest. In summary, Saturn is a planet where time moves strangely. Days are short, years are long, and the seasons linger for nearly a decade. Its rapid spin distorts its shape, making it visibly flattened at the poles, and its distance from the Sun stretches its orbit into a slow, stately progression through the sky. These features give Saturn its unique rhythm and help explain why it looks and behaves the way it does. They also remind us that the concept of normal planetary motion is defined only by Earth's experience. Out in the solar system, time and shape take on forms far beyond our everyday expectations. Saturn's atmosphere is both simple in its main ingredients and complex in its behavior. Like Jupiter, it is made almost entirely of hydrogen and helium, the 2 lightest and most abundant elements in the universe. Hydrogen makes up about 96% of the atmosphere, while helium contributes around 3%. The remainder consists of trace amounts of methane, ammonia, water vapor, and other gases, which, although tiny in proportion, play an outsized role in shaping the planet's appearance and weather. These ingredients are the same as those found in stars, which highlights Saturn's origin. It did not ignite into a star because it did not accumulate enough mass to trigger nuclear fusion, but it formed in the same general way, by gathering gas and dust from the early solar nebula. Its atmosphere, therefore, is a window into the raw materials of planet and star formation. Saturn's outer atmosphere is composed of several layers of clouds, stacked by altitude and temperature. At the highest levels where temperatures are coldest, ammonia ice forms the uppermost cloud deck. Beneath that, deeper in the atmosphere where conditions are warmer, scientists expect to find clouds of ammonium hydrosulfide. Still deeper, near the base of the weather layer are water ice clouds, which may also include droplets of liquid water under the extreme pressures. The arrangement of these clouds is theoretical in part, based on models and indirect observations, since spacecraft cannot penetrate to great depths without being destroyed. The cloud layers create Saturn's muted, banded appearance. Unlike Jupiter, which has bold stripes of brown, white, red, and orange, Saturn's bands are pale and subtle, appearing as shades of yellow, beige, and light brown. This is partly due to differences in composition. Saturn has less colorful chemical compounds in its atmosphere, and its cloud layers are covered by a high-altitude haze that blurs their contrasts. Cassini revealed that under certain lighting conditions, more details become visible, including small-scale storms and turbulence hidden beneath the hazy veil. Saturn's atmosphere also contains methane, though in small amounts. Methane absorbs red light, which is why in some wavelengths, Saturn appears slightly bluer than in visible light. Ammonia and trace hydrocarbons, produced by sunlight interacting with methane, add further complexity, contributing to the faint colors and haze. Photochemistry in Saturn's upper atmosphere creates a range of compounds that slowly drift downward, shaping the look of the cloud tops. One of the most striking properties of Saturn's atmosphere is how deep it extends. Unlike Earth, which has a relatively thin layer of air compared to its size, Saturn's atmosphere blends seamlessly into the rest of the planet. There is no solid surface, so defining where the atmosphere ends and the interior begins is difficult. Scientists usually measure Saturn's atmosphere at the point where the pressure reaches 1 bar, roughly the air pressure at Earth's surface. But beneath that level, the atmosphere continues downward for tens of thousands of kilometers, growing denser and hotter until hydrogen itself changes state. Despite its composition being mostly hydrogen and helium, Saturn is not chemically uniform. Cassini found that the upper atmosphere has less helium than expected compared to hydrogen. This supports the idea that helium slowly separates from hydrogen deeper down and sinks toward the core, releasing energy in the process. This helium rain may explain why Saturn radiates more heat than it receives from the Sun. The details of how this separation works are still an active area of research, but it shows that Saturn's atmosphere is dynamic, not only at the surface, but deep within. The atmosphere is also dynamic in another way. It is constantly in motion. Winds on Saturn are among the fastest in the solar system, reaching up to 1,800 kilometers per hour, 1,100 miles per hour, near the equator. These winds are powered by a combination of heat from the sun, internal heat from the planet's core, and the planet's rapid rotation. The result is a system of jet streams circling the planet, forming the bands we see in telescopes. These winds not only shape the bands, but also feed into massive storms, some of which last for years and cover thousands of kilometers. In addition to its clouds and winds, Saturn's upper atmosphere displays auroras, glowing light shows near the poles created when charged particles from the solar wind interact with the planet's magnetic field. Cassini and the Hubble Space Telescope have both observed Saturn's auroras, which are similar in principle to Earth's northern and southern lights, but much larger and more energetic. These auroras reveal how Saturn's atmosphere interacts with space around it, connecting the planet's deep interior to the solar wind billions of kilometers away. In summary, Saturn's atmosphere is a complex mixture of simplicity and subtlety. At its heart, it is mostly hydrogen and helium, yet the layering of clouds, the faint hues of trace gases, and the extraordinary winds make it a dynamic and fascinating system. It is less colorful than Jupiter, but no less active, with mysteries ranging from helium rain deep inside to auroras at the edge of space. Studying Saturn's atmosphere gives scientists not only a better understanding of gas giants, but also a clearer picture of how planets and stars form and evolve throughout the universe. One of the most remarkable features of Saturn's atmosphere is the sheer speed of its winds. At the equator, winds can reach 1,800 kilometers per hour, or about 1,100 miles per hour. To put that in perspective, the strongest hurricanes on Earth rarely exceed 300 kilometers per hour, 186 miles per hour. Saturn's jet streams are therefore among the fastest sustained winds in the solar system, rivaled only by those of Neptune. These winds are not isolated gusts, but enormous bands of air flowing around the planet in opposite directions, wrapping completely around the globe. The winds are driven by a combination of factors. Saturn rotates quickly, completing a full turn in just over 10.5 hours. This rapid rotation creates strong Coriolis forces, which deflect winds into east-west directions and give rise to the alternating bands of jet streams. At the same time, Saturn generates significant internal heat, radiating more energy into space than it receives from the Sun. This extra energy rises through the atmosphere, fueling convection, which in turn drives air circulation. The result is a complex system where rotation and convection combine to produce powerful and long-lasting winds. The jet streams are visible as bands across Saturn's disk. Unlike the dramatic contrasts of Jupiter's atmosphere, Saturn's bands are muted, with pale shades of yellow, beige, and brown. The difference lies partly in the upper haze covering Saturn's clouds, which softens the appearance of the bands. Still, the bands are real and represent zones where winds blow eastward or westward at different speeds. Cassini's observations showed that these jets extend deep into the atmosphere, though just how far down they reach is still debated. If the winds are shallow, confined to the upper layers of the atmosphere, they are mostly atmospheric phenomena. If they extend thousands of kilometers inward, they could be linked to Saturn's internal rotation and structure. Saturn's winds are not only fast, but also remarkably stable. Some jet streams have been observed in the same positions for decades, showing that the planet's atmosphere can maintain patterns on timescales far longer than any weather system on Earth. This stability is partly due to Saturn's size. On Earth, geography, mountains, oceans, continents, disrupts atmospheric flows and forces change. Saturn, with no solid surface, has no such interruptions. Its winds can circle the planet endlessly, shaped only by internal heat and the pull of gravity. The equatorial jet is particularly strong. Flowing eastward, it dominates Saturn's equatorial region, dwarfing any comparable jet stream on Earth. Above and below this equatorial jet, alternating bands of westward and eastward winds create a striped pattern that circles the entire planet. Cassini captured detailed images of these jets, revealing waves and vortices along their boundaries, evidence of turbulence where streams of air at different speeds collide. The winds also play a role in Saturn's storms. When jet streams interact or when rising heat from the interior disturbs them, massive storms can form, spanning thousands of kilometers. These storms often appear as bright white spots, known as great white spots, that can persist for months or even years. They are visible even through small telescopes on Earth, standing out against Saturn's otherwise muted atmosphere. The storms eventually break apart and fade, but the jet streams remain, ready to generate the next outbreak. Saturn's winds also help shape unique phenomena at the poles. The most famous of these is the hexagon at the North Pole, a six-sided jet stream discovered by Voyager in the 1980s and studied in detail by Cassini. The hexagon is not a separate storm, but part of the global circulation system, a standing wave in the atmosphere, locked into place by Saturn's rotation and winds. It shows how the planet's jet streams can organize into patterns with almost geometric precision. The depth of Saturn's winds is one of the ongoing puzzles of planetary science. Cassini's gravity measurements suggest that the winds may extend as much as 9,000 kilometers, 5,600 miles, beneath the cloud tops, carrying enough mass to affect the planet's gravitational field. This indicates that Saturn's atmosphere is far more connected to its interior than scientists once thought. Understanding these deep winds is crucial for learning how Saturn rotates internally, since the magnetic field, unlike Jupiter's, does not provide a clear rotation marker. On Earth, winds are temporary, shaped by the constant tug-of-war between ocean, land, and atmosphere. On Saturn, winds are part of the planet's permanent identity, sculpting its appearance and driving its weather. They are a reminder that gas giants are worlds where motion itself is a defining feature, where the flow of hydrogen and helium replaces mountains and oceans as the landscape. Saturn's winds are not just storms to be endured, but the very fabric of the planet, a system of endless motion powered by the rotation of a giant. Saturn is often described as a calm-looking planet compared to Jupiter, but that impression is misleading. While its bands are paler and its clouds more subtle, Saturn is capable of producing some of the most powerful storms in the solar system. These storms erupt from deep within its atmosphere, fueled by rising heat from the planet's interior, and can grow so large they become visible from Earth through modest telescopes. When they appear, they reveal that beneath Saturn's golden haze lies a turbulent and dynamic world. One of the most famous types of storms on Saturn is the Great White Spot. These are massive, bright storm systems that erupt roughly once every Saturn year, or about every 30 Earth years. The storms are so large that they can stretch across the entire planet, covering distances of tens of thousands of kilometers. The most recent one occurred in 2010 and was extensively observed by Cassini as well as ground-based telescopes. It began as a bright patch of clouds near the northern mid-latitudes and quickly grew, eventually circling the entire planet. At its peak, it was visible even with small backyard telescopes, a striking white scar against Saturn's soft bands. The energy behind these storms comes from the combination of Saturn's internal heat and the buildup of energy in its deep atmosphere. Saturn radiates more than twice the energy it receives from the Sun, and this heat works its way upward through the atmosphere. Over decades, energy accumulates until it bursts through in an enormous convective event, the Great White Spot. The storms not only release heat, but also churn the atmosphere, redistributing chemicals and creating turbulence that lasts for years. Cassini's instruments detected ammonia and water being dredged up from deeper layers during the 2010 storm, offering clues about Saturn's interior processes. Beyond the Great White Spots, Saturn is constantly dotted with smaller storms and vortices. Cassini observed countless bright spots that lasted for weeks or months, storms thousands of kilometers wide but small compared to the planet itself. These storms often form in the turbulent zones where jet streams collide, similar to how hurricanes on Earth feed off the interaction of warm air and rotation. Unlike Earth's hurricanes, however, Saturn's storms have no oceans to fuel them. Instead, they draw their power from rising columns of warm gas and the immense reservoir of energy in Saturn's depths. At the poles, Saturn shows a different kind of weather system. The North Pole is home to the famous hexagon, a jet stream shaped into a six-sided figure over 30,000 kilometers, 18,600 miles, across. Within the hexagon lies a giant polar vortex, a swirling storm system several times larger than Earth. The South Pole has its own vortex, a massive storm with a clearly defined eye, much like a hurricane, but on a far grander scale. Unlike hurricanes on Earth, which fade when they move over land or lose their heat source, Saturn's polar vortices appear to be permanent, sustained by the dynamics of the planet's atmosphere. Cassini's images showed clouds swirling deep into the vortex, with wind speeds over 500 kilometers per hour, 310 miles per hour. Saturn's storms are not just impressive in size, they also alter the chemistry of the atmosphere. Cassini's instruments detected that lightning within the storms produces new molecules, including hydrocarbons, which add to the hazes in the upper atmosphere. Saturn's lightning storms are powerful enough to be detected from Earth using radio telescopes, even when the storms themselves are hidden beneath the planet's clouds. These detections, called Saturn electrostatic discharges, were first observed by Voyager and later tracked in detail by Cassini, confirming that Saturn's storms can rival or exceed those on Earth in terms of electrical energy. The interplay between Saturn's storms and its long seasons also creates unique patterns. Because Saturn's year lasts nearly 30 Earth years, each season stretches out for more than 7 years. Seasonal changes affect how sunlight strikes the atmosphere, altering temperatures and circulation. During Cassini's mission, which lasted over 13 years, scientists were able to watch as the planet shifted from northern winter into summer. This provided unprecedented insight into how Saturn's weather evolves on timescales far longer than Earth's. The 2010 Great White Spot, for instance, coincided with the onset of northern summer, suggesting a connection between the buildup of energy during winter and the explosive release when sunlight returned. Storms also leave scars on Saturn's atmosphere. After the 2010 storm subsided, Cassini detected chemical changes that lingered for years, including elevated levels of ethylene, a hydrocarbon gas rarely found in such abundance on giant planets. The storm also disrupted Saturn's jet streams, showing that even features thought to be stable can be reshaped by massive convective outbursts. In many ways, Saturn's weather teaches scientists about atmospheric dynamics under conditions very different from Earth's. On our planet, storms are driven by water, continents, and the interaction of land and sea. On Saturn, there is no solid surface, and storms emerge from vast layers of hydrogen and helium. Yet the same principles of fluid dynamics apply. Heat rises, rotation shapes, winds, and turbulence creates vortices. By studying Saturn, scientists gain new perspectives on how atmospheres work, not just in our solar system, but across the universe, including on exoplanets orbiting distant stars. Saturn may look tranquil from afar, with its pale bands and graceful rings, but up close, it is a world of tempests. Its storms erupt with a force that dwarfs anything on Earth, reshaping the atmosphere and revealing the raw power of a planet made mostly of gas. Each storm is both a scientific opportunity and a reminder that Saturn is far from serene. It is a restless giant where energy builds silently for decades before exploding into storms that can encircle the entire world. Among all the strange and beautiful phenomena in the solar system, few are as visually striking and mysterious as Saturn's North Polar Hexagon. First discovered in the early 1980s by the Voyager spacecraft, the feature baffled scientists and immediately captured the imagination of the public. It looks almost artificial, a perfect six-sided pattern encircling the North Pole, large enough to swallow Earth whole. The hexagon is not a surface feature, nor is it a solid structure. It is a jet stream, a current of atmosphere shaped into an immense polygon by the dynamics of Saturn's rotation and winds. The hexagon spans about 30,000 kilometers, 18,600 miles, across, more than twice the diameter of Earth. Each side is roughly 14,000 kilometers, 8,700 miles long, longer than the width of our entire planet. Within the hexagon lies a massive polar vortex, a storm system spinning deep into the atmosphere, with winds exceeding 500 kilometers per hour, 310 miles per hour. The scale of the hexagon is staggering. It is not just a local weather pattern, but a planetary scale circulation, locked into place at the North Pole. Voyager's discovery showed the hexagon in black and white images, but it was Cassini, arriving at Saturn in 2004, that revealed its full complexity. Cassini observed the hexagon for more than a decade, capturing images in visible light, infrared, and ultraviolet. These showed that the hexagon is not only long-lasting, but also extends deep into the atmosphere. Unlike transient storms or waves that dissipate, the hexagon persisted throughout Cassini's entire mission, demonstrating extraordinary stability. What causes such a precise geometric shape? The leading explanation is that the hexagon is a standing wave in Saturn's atmosphere. On Earth, fluids and gases can form polygonal patterns when rotating in a controlled environment, such as in laboratory experiments with rotating tanks of water. In Saturn's case, the planet's rapid rotation and powerful winds combine to form a jet stream at the North Pole. Instabilities in this jet stream can lock into place, creating wave patterns. For reasons not entirely understood, the wave at Saturn's pole has stabilized into a six-sided polygon. The hexagon is also unusual because of its symmetry. While atmospheric waves are common in planetary atmospheres, they rarely form such perfect and persistent geometric figures. On Earth, for instance, polar jet streams form meandering loops but never lock into regular shapes. Saturn's hexagon demonstrates that in the extreme conditions of a gas giant, rapid rotation, deep atmosphere, and immense scale, fluid dynamics can behave in ways far removed from our terrestrial experience. Cassini's observations also revealed seasonal changes in the hexagon. When the spacecraft arrived, the North Pole was in winter darkness, and the hexagon was only visible in infrared. As Saturn moved through its seasons and the northern hemisphere tilted toward the sun, the hexagon gradually came into visible light. By 2017, when Cassini ended its mission, the hexagon was fully illuminated, and scientists could see it in detail across multiple wavelengths. They found that the colors within the hexagon changed with the seasons, likely due to photochemical reactions in the atmosphere as sunlight returned. In winter, the hexagon appeared bluish in infrared images, while in summer it took on a more golden hue, blending with the rest of Saturn's atmosphere. At the center of the hexagon lies a storm unlike any other in the solar system, a polar vortex with a well-defined eye. Cassini's close-up images showed that the vortex resembles a hurricane on Earth, with spiraling clouds and an open center. But this storm is far larger and longer-lived than any hurricane. Its eye is about 2,000 kilometers, 1,250 miles, across, wide enough to fit two Earths side by side. Unlike terrestrial hurricanes, which weaken when cut off from warm ocean water, Saturn's polar vortex is sustained indefinitely by the dynamics of the planet's atmosphere. It appears to be a permanent feature, as stable as the hexagon that surrounds it. The persistence of the hexagon raises deep questions about Saturn's atmosphere. How can a structure this large and complex remain stable for decades or even centuries? Laboratory experiments and computer simulations can reproduce polygonal jet streams under controlled conditions, but scaling these models up to Saturn's size is difficult. Some theories suggest that the hexagon is linked to oscillations deep in the atmosphere, extending thousands of kilometers below the clouds. Others argue that it is a surface phenomenon confined to the upper layers, sustained by the balance of winds and waves. Either way, the hexagon remains one of the best natural laboratories for studying fluid dynamics on a planetary scale. Beyond its scientific significance, the hexagon is one of Saturn's most iconic features. It is a reminder that nature often produces patterns that seem almost too precise to be natural. A six-sided storm at the top of a planet more than 1 billion kilometers from Earth challenges our sense of what is ordinary and possible. It also demonstrates how far space exploration has come. What was once a fuzzy black and white image from Voyager became a richly detailed, multi-wavelength study thanks to Cassini. The hexagon stands as both a scientific puzzle and a symbol of Saturn's strangeness. In the years since Cassini's mission ended, the hexagon remains a subject of study through ground-based telescopes and computer models. Future missions to Saturn may one day return to study it in greater detail, perhaps even dropping probes into the atmosphere to measure the winds directly. Until then, the hexagon remains one of the most striking examples of planetary weather, a storm system so vast and precise that it seems to blur the line between science and art. While Saturn is most famous for its rings and atmosphere, it also possesses a powerful magnetic field that shapes its environment in ways invisible to the eye but critical for understanding the planet. Magnetic fields arise when charged particles move in a conducting medium, and in Saturn's case, this happens deep within the planet, where hydrogen is compressed into a metallic state under immense pressure. The movement of this metallic hydrogen generates a dynamo effect, producing a magnetic field that extends millions of kilometers into space. Saturn's magnetic field is not as strong as Jupiter's, but is still enormous compared to Earth's. At the equator, it is about 20 times stronger than Earth's field, enough to trap charged particles and create radiation belts. These belts, however, are weaker than Jupiter's lethal zones, which makes Saturn's environment less hostile to spacecraft. For missions like Cassini, this was a critical advantage, allowing it to orbit Saturn for over a decade without being destroyed by radiation. One of the strangest features of Saturn's magnetic field is its symmetry. On Earth and Jupiter, the magnetic poles are tilted relative to the planet's rotation axis. This tilt allows scientists to measure the length of a planet's day by tracking how the magnetic field wobbles as the planet spins. But Saturn's magnetic field is almost perfectly aligned with its rotation axis to within 0.06 degrees. This unusual alignment means that the field doesn't wobble, making it extremely difficult to determine Saturn's true rotation rate. Cassini tried repeatedly to resolve this mystery, but by the time the mission ended in 2017, the planet's exact rotation period was still uncertain by several minutes. For a planet studied so extensively, this basic detail remains elusive. Saturn's magnetic field also creates dazzling auroras at the poles, similar to Earth's northern and southern lights, but on a far grander scale. These auroras occur when charged particles from the solar wind, or from Saturn's own moons like Enceladus, funnel along magnetic field lines and collide with gases in the atmosphere. The collisions excite atoms and molecules, causing them to emit light. Observations from Cassini and the Hubble Space Telescope revealed auroras stretching thousands of kilometers, glowing in ultraviolet and infrared, as well as visible light. Unlike Earth's auroras, which are strongly influenced by the solar wind, Saturn's auroras are more complex, with contributions from both the Sun and the planet's internal processes. The magnetosphere, the region dominated by Saturn's magnetic field, is immense. On the side facing the Sun, the solar wind compresses it to about 1.2 million kilometers, 750,000 miles from the planet. On the side away from the Sun, the magnetotail stretches for millions of kilometers into space, forming a vast comet-like tail. Within this region, charged particles are trapped and accelerated, bouncing back and forth along field lines. Cassini measured the composition of these particles and found they often included water vapor and ice grains from Enceladus, whose geysers eject material that becomes electrically charged and incorporated into Saturn's magnetic environment. This connection between a moon and a planetary magnetosphere is unique and demonstrates how tightly linked Saturn and its satellites are. Radiation within Saturn's magnetosphere can be intense, though not as extreme as around Jupiter. For humans, the environment would still be hazardous without shielding, but it is survivable for spacecraft over long periods. Cassini's long life at Saturn is proof of this. Instruments on board were able to measure not just radiation levels, but also the way the magnetosphere interacts with the rings and moons. For example, Cassini observed how charged particles struck Saturn's rings, creating glowing bands of ultraviolet light called ring rain. These interactions mean that Saturn's rings are not static ornaments, but active participants in the planet's magnetic environment. The alignment of Saturn's magnetic field has broader implications for planetary science. Dynamo theory suggests that perfect alignment should not be stable over billions of years. Yet Saturn's field is nearly symmetrical, raising questions about how its internal dynamo works. Some researchers propose that helium rain deep inside the planet alters the circulation of metallic hydrogen, producing an unusually stable field. Others suggest that the field may be slowly changing in ways we have not yet observed. Whatever the explanation, Saturn challenges our understanding of how giant planets generate and maintain magnetic fields. The study of Saturn's magnetosphere is also a bridge to exoplanet research. Many exoplanets discovered so far are gas giants, orbiting close to their stars, where magnetic interactions could dominate their atmospheres. Understanding Saturn's field gives scientists a model for how magnetic environments work in large planets, even those very different from our solar system. The way Saturn's field interacts with its moons, particularly Enceladus, also highlights the importance of magnetospheres in shaping the habitability of nearby worlds. In summary, Saturn's magnetic field is less dramatic than Jupiter's, but no less fascinating. Its near-perfect alignment remains a puzzle, its auroras are spectacular, and its magnetosphere connects the planet to its rings and moons in a dynamic system. Invisible to the naked eye, the field is nonetheless a defining feature of Saturn, shaping everything from spacecraft navigation to the potential habitability of moons like Enceladus. It is a reminder that what we see, rings, bands, and storms, is only part of the story, and that the unseen forces around Saturn are just as vital to understanding this giant world. Saturn's rings are the most recognizable and spectacular feature in the solar system. Even through a small telescope, they transform Saturn from another distant planet into an icon of astronomy. They span hundreds of thousands of kilometers across, but are astonishingly thin, with an average thickness of only about 10 meters, 33 feet in many places. This combination of vast scale and fragile delicacy makes them one of the most unique structures known in planetary science. The main rings are divided into several major sections: the A ring, B ring, and C ring, with smaller, fainter rings, both inside and outside these main bands. The Cassini division, a dark gap about 4,800 kilometers, 3,000 miles, wide, separates the A and B rings and is easily visible in telescopic images. Beyond the A ring lies the thin F ring, a narrow but highly dynamic feature that shifts and twists under the influence of nearby moons. Farther still are faint, dusty rings, such as the G and E rings, each maintained by the activity of specific moons. The sheer size of the rings is difficult to grasp. From edge to edge, they extend about 282,000 kilometers, 175,000 miles, which is nearly 3/4 of the distance from Earth to the Moon. Yet despite their scale, they are incredibly thin, like a sheet of paper stretched across the length of a football field. If Saturn's rings were shrunk down to that size, they would be thinner than a human hair. This fragility is part of what makes them so remarkable. Something so large and bright can also be so insubstantial. The rings are not solid, but made of countless particles, ranging from dust-sized grains to chunks the size of houses. Most of these particles are water ice, mixed with small amounts of rock and dust. Their icy composition explains why the rings are so reflective, shining brightly in sunlight and making Saturn one of the most luminous objects in the night sky. The particles move in orbit around Saturn, according to Kepler's laws, with those closer to the planet moving faster than those farther away. This creates the flat disc-like shape of the rings, and also explains why they are divided into bands and gaps. The age of Saturn's rings remains one of the most debated questions in planetary science. For decades, scientists assumed the rings were as old as Saturn itself, forming over 4 billion years ago, along with the planet. But data from the Cassini mission suggests they may be much younger, perhaps only 100 to 200 million years old. The key evidence is their brightness. Over time, icy rings should become polluted by dark dust from space, yet Saturn's rings remain remarkably clean and reflective. This suggests they may have formed relatively recently, possibly from the breakup of a moon or a comet that wandered too close and was torn apart by Saturn's gravity. Cassini's close-up observations showed that the rings are not uniform. They contain waves, ripples, and clumps caused by the gravitational influence of Saturn's moons. These moons act as shepherds, shaping and sculpting the rings. The tiny moon Pan, for example, orbits within the Encke gap of the A ring, keeping the gap clear and creating sharp edges. Prometheus and Pandora flank the narrow F ring, tugging its material into streamers and knots. The rings, therefore, are not static structures, but dynamic systems, constantly reshaped by gravitational interactions. Saturn's rings also interact with the planet itself. Cassini discovered that charged particles from the rings rain down onto Saturn's atmosphere, influencing its ionosphere and possibly its weather. This ring rain shows that the rings are not eternal. Over time, their material is gradually lost, either falling onto Saturn or being ejected into space. This means that the rings we see today will not last forever. On geological timescales, they may disappear entirely, leaving Saturn as just another gas giant. Despite this eventual fate, Saturn's rings today remain one of the most stunning natural features in existence. They combine vastness and fragility, permanence and impermanence, simplicity and complexity. They are both a symbol of Saturn and a laboratory for studying how gravitational and orbital forces shape matter in space. Whether ancient or young, enduring or fleeting, the rings remind us that planetary systems are not static but constantly evolving. The overview of Saturn's rings sets the stage for deeper exploration. In the following sections, we will examine the structure of the main rings in more detail, the role of moons in sculpting them, the mysteries of their age and origin, and the dynamic processes that keep them in motion. The rings are not just decorations. They are windows into the processes that shape planets, moons, and even entire solar systems. The rings of Saturn may appear smooth and uniform from a distance, but up close, they are divided into a complex system of bands, gaps, and divisions. The main rings, labeled A, B, and C, are the most prominent and were the first to be studied in detail. Together, they form the dazzling system easily visible through telescopes. Yet each ring has its own character, shaped by gravity, orbital mechanics, and the subtle influences of Saturn's moons. The innermost of the three is the C ring, sometimes called the crepe ring because of its faint and semi-transparent appearance. It lies just inside the massive B ring, extending from about 74,500 kilometers, 46,300 miles, to 92,000 kilometers, 57,200 miles above Saturn's cloud tops. The C ring is relatively thin and dusty, with lower reflectivity than the other main rings. It contains several faint structures known as plateaus, where brightness and particle density vary. These features were revealed in detail by Cassini, which also found that parts of the C ring interact strongly with Saturn's magnetic field, creating patterns linked to oscillations inside the planet itself. In a sense, the C ring acts like a seismograph, recording Saturn's internal vibrations in the form of ripples. Beyond the C ring lies the B ring, the largest and brightest of all. Spanning from 92,000 kilometers, 57,200 miles, to 117,500 kilometers, 73,000 miles, above Saturn, the B ring dominates the planet's appearance. It is dense and reflective, containing a huge portion of the total mass of the ring system. The B ring is so thick with particles that in many places it is almost opaque, blocking sunlight from passing through. Cassini's images showed that the B ring is riddled with radial features known as spokes, which appear as dark streaks extending across the ring. These spokes are thought to be caused by electrostatic charges lifting fine dust particles above the ring plane, though the exact mechanism remains uncertain. The B ring is also home to density waves and bending waves created by gravitational interactions with Saturn's moons. These wave patterns ripple through the ring like frozen echoes of orbital resonances. Next comes the Cassini division, the most famous gap in the rings, lying between the B and A rings. About 4,800 kilometers, 3,000 miles wide, it looks like a clean, empty space when viewed through a telescope. But Cassini revealed it is not empty at all. Instead, it contains a sparse population of ring particles, sculpted by a resonance with the moon Mimas. At this resonance, particles orbit Saturn twice for every orbit of Mimas, causing Mimas's gravity to tug them repeatedly and clear out much of the material. The Cassini division is thus a striking example of how moons can shape the rings from afar, leaving visible scars in their structure. Outside the Cassini division lies the A ring, the outermost of the main trio. It extends from about 122,000 kilometers, 76,000 miles, to 137,000 kilometers, 85,000 miles, above Saturn's clouds. The A ring is less dense than the B ring, but still bright, and it is home to several notable features. The most famous is the Encke Gap, a narrow 325-kilometer, 200-mile wide opening containing the tiny moon Pan. Pan acts as a shepherd, sweeping the gap clear of particles and sculpting sharp edges along its borders. Another feature is the Keeler Gap, even narrower at just 42 kilometers, 26 miles wide, containing the moon Daphnis, which creates rippling waves along the edges of the gap as it orbits. These embedded moons highlight how delicate gravitational balances maintain the ring system's intricate patterns. The A ring also shows spiral density waves, alternating bands of high and low particle density, caused by resonances with moons farther away. These spirals act like frozen sound waves, marking the transfer of energy from moons to ring particles. In some cases, the waves are linked to Saturn's own oscillations, meaning the rings can tell scientists about vibrations deep within the planet, a field of study known as chronoseismology. Through these vibrations, researchers can infer details about Saturn's interior that would otherwise be hidden beneath the clouds. Taken together, the C, B, and A rings form the heart of Saturn's system, spanning tens of thousands of kilometers and containing billions of icy particles. Their sharp edges, gaps, and internal structures are evidence of constant sculpting by gravity and resonance. Rather than being static, they are dynamic environments where moons, magnetic fields, and Saturn's own oscillations leave their imprints. The complexity of the main rings raises an important point. The system is not simply a disk of material, but a record of Saturn's history. Each gap tells a story of gravitational tug-of-war. Each wave records the pull of a moon or the vibrations of the planet itself. Each spoke reflects interactions between dust and magnetism. The rings are not only beautiful, they are archives of motion and change. This close look at the main rings is just the beginning. Outside them lies the narrow F ring and the faint distant rings maintained by Saturn's smaller moons. These outer regions are less massive, but even more dynamic, showcasing how moons and rings interact in surprising ways. To understand the whole system, we need to move outward and examine the delicate structures that complete Saturn's crown. If the A, B, and C rings form the solid foundation of Saturn's system, the outer rings are where things get more delicate, dynamic, and surprising. These rings are faint, narrow, and often unstable, but they reveal processes that keep the entire system alive. Among them, the F ring stands out as one of the most fascinating features in planetary science. The F ring lies just beyond the A ring, at about 140,000 kilometers, 87,000 miles, from Saturn's cloud tops. Unlike the broad, dense bands of the main rings, the F ring is extremely narrow, only a few hundred kilometers wide. But within that narrow band lies a constantly changing landscape of braids, knots, and clumps. Cassini's close-up images showed the F ring twisting and bending, its structure shifting over the course of hours and days. It is a ring in constant motion, reshaped by the tug of nearby moons. Two small moons, Prometheus and Pandora, flank the F ring and act as its shepherds. Their gravity confines the ring's particles, preventing them from spreading outward into space. But the moons do more than just shepherd the ring. They disturb it. As Prometheus moves along its slightly eccentric orbit, it passes close to the ring, pulling streamers of material out and leaving behind gaps and clumps. Pandora, orbiting just beyond the ring, exerts its own pull, adding to the chaos. The result is a ring that never looks the same twice. Cassini observed the F ring producing new clumps and strands, only for them to disperse weeks later. It is as if the ring is constantly creating and destroying itself under the moon's gravitational influence. The F ring is also a site of collisions. Some of its particles coalesce into temporary moonlets, small clumps of ice only a few kilometers across. These moonlets often do not last long. They are either disrupted by collisions or pulled apart by the tidal forces of Saturn and its shepherd moons. But for a time, they can sculpt the ring, creating channels, ripples, and bright streaks. Cassini captured dramatic images of such events, showing bright jets of material being flung outward as moonlets collided with the ring. These collisions highlight how Saturn's rings are not static relics, but dynamic systems still undergoing change. Beyond the F ring lie several fainter, more diffuse rings. The G ring, about 170,000 kilometers, 106,000 miles, from Saturn, is a narrow band of dust. It is maintained by the tiny moon Aegeon, which orbits within the ring. Micrometeoroid impacts on Aegeon release material that feeds the ring, keeping it replenished. Without this source, the dust would quickly disperse into space, so the moon's presence ensures the G ring's survival. Even farther out is the E ring, one of the largest and most unusual in the solar system, stretching from about 180,000 kilometers, 112,000 miles, to nearly 1,000,000 kilometers, 620,000 miles from Saturn. The E ring is diffuse and faint, made of microscopic ice grains. Its source is the moon Enceladus. Cassini discovered geysers erupting from Enceladus's south pole, spraying water vapor and ice into space. This material escapes the moon's weak gravity and spreads out along its orbit, forming the E ring. It is the only known example in the solar system of a moon actively supplying a planet's rings. The E ring is therefore both a product of Enceladus and a key to its habitability, since the geysers hint at a subsurface ocean beneath the icy crust. The outermost rings are even more tenuous. The Phoebe ring, discovered in 2009, is a vast but nearly invisible structure extending millions of kilometers from Saturn. It is fed by dust from the irregular moon Phoebe, far beyond the main ring system. The ring is so faint that it can only be detected with infrared observations, but it is immense, stretching outward nearly 200 times farther than the main rings. The particles in the Phoebe ring are dark, unlike the icy brightness of the inner rings, and some of this material may be responsible for coating the surface of another moon, Iapetus, giving it its striking two-toned appearance. Taken together, Saturn's outer rings show how moons and rings are linked in constant cycles of creation and destruction. The F ring demonstrates how shepherd moons sculpt and disturb material. The G ring shows how a single small moon can feed and maintain a ring. The E ring proves that active geology on a moon can build an entire planetary feature. And the Phoebe ring extends the system outward to nearly unimaginable scales, connecting the inner planet to its distant, irregular satellites. What makes the outer rings especially compelling is their fragility. They are not permanent structures like mountains or oceans, but temporary features, maintained only as long as their moons provide material. Without the shepherding and feeding from these satellites, the rings would disperse within a few thousand years. In this sense, Saturn's rings are not only beautiful, but fleeting, a cosmic balance that will one day fade. For now, however, they stand as one of the most extraordinary spectacles in the solar system, their dynamic interplay between moons and particles revealing the intricate dance of gravity and time. Saturn is not only the lord of the rings, but also the keeper of a vast and diverse collection of moons. As of now, astronomers have confirmed more than 140 moons orbiting Saturn, more than any other planet in the solar system. They range in size from tiny, irregular chunks of ice and rock, only a few kilometers wide, to Titan, a world larger than Mercury with a thick atmosphere and active geology. Together, they form a miniature solar system, each moon with its own story and role in shaping Saturn's environment. The largest and most famous of Saturn's moons is Titan. With a diameter of 5,150 kilometers, 3,200 miles, it is bigger than the planet Mercury and about 50% larger than Earth's moon. Titan is unique in that it has a dense atmosphere, composed mostly of nitrogen with traces of methane and other hydrocarbons. This atmosphere supports a methane cycle similar to Earth's water cycle, with clouds, rain, rivers, lakes, and seas, except made of liquid methane and ethane. Beneath its icy surface, Titan is also thought to harbor a subsurface ocean of liquid water mixed with ammonia, making it one of the prime candidates in the search for extraterrestrial life. The second most celebrated moon is Enceladus, a small world only 504 kilometers, 313 miles across. Despite its modest size, Enceladus is geologically active, with geysers erupting from fractures near its south pole. These geysers spray water vapor and ice particles into space, feeding Saturn's E-ring and hinting at a global subsurface ocean. Cassini flew through these plumes and detected organic molecules, salts, and even hints of hydrothermal activity on the ocean floor. This makes Enceladus another prime target in the search for life, despite its tiny scale. Rhea, Dione, and Tethys are mid-sized icy moons, each between 1,000 and 1,500 kilometers, 620 to 930 miles, across. They are heavily cratered, with ancient surfaces recording billions of years of impacts. Yet each has its quirks. Dione shows evidence of past geological activity in the form of bright streaks of icy cliffs. Tethys has a massive valley system called Ithaca Cosma, stretching 2,000 kilometers, 1,200 miles, across its surface. Rhea may even have faint rings of its own, though this remains debated. These moons illustrate the diversity of geological processes that have shaped Saturn's system over time. Iapetus stands out for its striking two-toned appearance. One hemisphere is bright and reflective, covered in ice, while the other is dark and coated with material thought to come from the distant Phoebe ring. Iapetus also has an equatorial ridge, a chain of mountains running along its middle like the seam of a baseball. The origin of this ridge remains a mystery, with theories ranging from ancient rings collapsing onto its surface to tectonic activity within the moon itself. Mimas is another notable member of Saturn's family, famous for its massive crater Herschel, which makes the moon resemble the Death Star from Star Wars. At 396 kilometers, 246 miles across, Mimas is relatively small, but its orbital resonances with other moons help shape Saturn's rings. For example, the Cassini division in the main rings exists because of Mimas's gravitational influence. Beyond these larger moons, Saturn has dozens of smaller satellites that play important roles in sculpting the rings. Pan and Daphnis orbit within gaps in the A ring, carving sharp edges and creating rippling waves in the ring material. Prometheus and Pandora flank the F ring, constantly disturbing its delicate strands. These so-called shepherd moons demonstrate how even small bodies, only tens of kilometers across, can have dramatic effects on Saturn's vast ring system. Still farther out, Saturn hosts a population of irregular moons, captured objects that orbit in distant, inclined, and sometimes retrograde paths. These moons are thought to be remnants of ancient collisions or captured asteroids from the early solar system. Phoebe, one of the largest irregular moons, orbits far beyond the main system and is the source of dust that creates the vast Phoebe ring. These outer moons show that Saturn's gravitational influence extends far into space, sweeping up stray objects and adding them to its retinue. Taken together, Saturn's moons form a system as complex and varied as the planets themselves. Titan and Enceladus capture the imagination because of their potential for habitability. Rhea, Dione, Tethys, and Iapetus showcase geological diversity. Mimas, Pan, and Prometheus reveal the delicate interplay between moons and rings. The irregular satellites extend Saturn's domain outward into the depths of space. Each moon is not only a world in its own right, but also a participant in the larger drama of Saturn, shaping and being shaped by the planet's gravity, magnetism, and rings. In the next sections, we will look more closely at individual moons, beginning with Titan, whose thick atmosphere and methane seas make it one of the most Earth-like and alien worlds in the solar system. From there, we will explore Enceladus and its geysers, followed by the rest of Saturn's remarkable satellite family. Titan, Saturn's largest moon, is one of the most extraordinary objects in the solar system. At 5,150 kilometers, 3,200 miles in diameter, it is bigger than the planet Mercury and about 1.5 times the size of Earth's moon. But size alone does not explain its significance. What makes Titan remarkable is its atmosphere, its surface activity, and its potential for harboring the building blocks of life. In many ways, Titan is both familiar and alien, echoing processes we recognize from Earth, but playing them out with different ingredients. Titan is the only moon in the solar system with a thick atmosphere. Its air is composed mostly of nitrogen, about 95%, with methane and other hydrocarbons making up most of the rest. The pressure at Titan's surface is about 1.5 times that of Earth's, comparable to standing a few meters underwater. This atmosphere creates a haze that makes Titan's surface invisible to visible light telescopes. For centuries, Titan was little more than a fuzzy orange orb, its surface hidden beneath a shroud of mist. Only when spacecraft began to visit did scientists finally peel back the layers and glimpse the world below. The first breakthrough came with the Voyager flybys in the 1980s, which revealed Titan's thick atmosphere but offered little detail. The real revelations came with the Cassini-Huygens mission. Cassini carried the European Space Agency's Huygens probe, which descended through Titan's atmosphere in January 2005. As Huygens parachuted down, it took images and measurements, providing the first direct look at Titan's surface. It revealed a landscape carved by rivers and valleys, with channels leading into broad floodplains. The probe landed on a flat, icy plain scattered with pebbles of water ice, confirming that Titan's surface is shaped by active processes. What Huygens and Cassini revealed was that Titan has a methane cycle, analogous to Earth's water cycle. On Earth, water evaporates, forms clouds, falls as rain, and collects in rivers, lakes, and oceans. On Titan, methane and ethane play the same role. Cassini's radar mapped vast seas of liquid methane and ethane in Titan's polar regions, some larger than the Great Lakes in North America. It also detected rainstorms, clouds, and river channels, showing that liquid still flows on Titan today. This makes Titan the only other world in the solar system with stable liquids on its surface. The temperatures on Titan are extreme by Earth standards, averaging around minus 179 degrees Celsius, minus 290 degrees Fahrenheit. At this temperature, water is frozen as hard as rock, and methane takes the role of liquid. The rocks on Titan are blocks of water ice, and the sand dunes are made of organic particles produced in the atmosphere. Cassini discovered vast dune fields stretching for hundreds of kilometers near the equator, shaped by Titan's winds. These dunes are made of complex hydrocarbons, giving Titan a surface rich in organic chemistry. Beneath Titan's icy crust, scientists believe there is a subsurface ocean of liquid water mixed with ammonia. Cassini measured subtle variations in Titan's gravity and rotation that suggest its icy shell is decoupled from the interior, a sign of a hidden ocean. If this ocean exists, it could provide the conditions for life as we know it: liquid water, organic molecules, and energy sources. This makes Titan not only fascinating as a world in its own right, but also a prime target in the search for extraterrestrial life. The atmosphere itself is a chemical factory. Ultraviolet light from the sun breaks apart methane molecules high in the atmosphere, triggering reactions that form complex hydrocarbons and nitriles. These molecules drift downward, forming the thick orange haze that blankets the moon. Some of them fall to the surface, where they may accumulate into deposits of organic-rich material. These processes may resemble the kinds of chemistry that occurred on early Earth before life began, offering a natural laboratory for studying prebiotic conditions. Titan is also geologically active in subtle ways. Cassini observed features on the surface that suggest cryovolcanism, eruptions of water and ammonia instead of molten rock. These cryovolcanoes, if they exist, could provide a way for material from the subsurface ocean to reach the surface, further enriching Titan's chemical environment. The combination of surface liquids, organic chemistry, and a possible interior ocean makes Titan unique among moons and planets alike. The exploration of Titan is far from over. While Cassini and Huygens provided a wealth of data, they only scratched the surface. In the coming decades, NASA's Dragonfly mission will return to Titan with a rotorcraft lander capable of flying through its thick atmosphere and exploring multiple sites on the ground. Scheduled to launch in the mid-2030s, Dragonfly will investigate Titan's chemistry, geology, and habitability in far greater detail than ever before. The mission could reveal whether Titan's surface and ocean contain the ingredients or even the processes necessary for life. Titan challenges our definition of habitability. On the surface, conditions are far too cold for life as we know it, yet the chemistry there mirrors many of the steps thought to have led to life on Earth. In the interior, a warm, salty ocean may harbor environments more directly compatible with biology. Titan therefore represents two laboratories in one: a frozen world with an active methane cycle on the surface and a hidden ocean below. Both environments could provide insights into how life begins and survives under conditions very different from Earth's. In summary, Titan is Saturn's most complex and Earth-like moon, though in a profoundly alien way. Its thick nitrogen atmosphere, methane lakes, hydrocarbon dunes, and possible water ocean make it one of the most intriguing worlds in the solar system. By studying Titan, scientists hope not only to understand this unique moon, but also to learn about the processes that shape planets, atmospheres, and even the origins of life itself. Titan is no mere satellite. It is a world, and one that may hold answers to some of humanity's oldest questions. If Titan is Saturn's most Earth-like moon, Enceladus is its most surprising. At just 504 kilometers, 313 miles in diameter, Enceladus is only about 1/7 the size of Earth's moon. For decades, it was assumed to be a frozen, geologically dead world. That assumption changed forever when the Cassini spacecraft revealed one of the most dramatic discoveries in planetary science. Enceladus is active, spraying plumes of water vapor and ice into space from its south pole. This revelation transformed Enceladus from a minor icy moon into one of the top contenders in the search for life beyond Earth. Enceladus reflects nearly all the sunlight that hits it, making it one of the brightest objects in the solar system. Its surface is covered in clean water ice, giving it a high albedo and a stark, almost pristine appearance. Cassini's close flybys revealed a surface divided into contrasting terrains, heavily cratered ancient regions, alongside younger areas marked by ridges, fractures, and smooth plains. These younger surfaces indicated that Enceladus had experienced geological activity in its recent history, a hint that something unusual was happening inside. The most spectacular evidence came in 2005 when Cassini detected plumes erupting from long fractures near the moon's south pole, nicknamed tiger stripes. These geysers spewed water vapor, ice particles, salts, and organic compounds into space, forming a giant plume that extended hundreds of kilometers above the surface. Cassini flew directly through these plumes multiple times, sampling their composition. The results were extraordinary. The plumes contained water, simple and complex organic molecules, carbon dioxide, methane, and ammonia, ingredients associated with habitability. Beneath the icy crust, scientists concluded Enceladus must have a subsurface ocean. Further analysis of the plumes showed evidence of tiny silica grains that could only have formed in hot water, interacting with rock at high temperatures. This pointed to hydrothermal vents on the seafloor of the hidden ocean, similar to those found in Earth's oceans. On Earth, hydrothermal vents support rich ecosystems of microbes and animals, thriving in the absence of sunlight. If similar conditions exist on Enceladus, life may be possible there as well. The plumes of Enceladus also help maintain Saturn's E-ring. Material ejected from the Moon escapes its weak gravity and spreads out along its orbit, forming a diffuse ring of fine ice grains. This makes Enceladus unique. It is not only shaped by Saturn, but also actively shaping Saturn's environment. Without Enceladus, the E-ring would quickly dissipate, proving that this small moon plays an outsized role in the planetary system. The discovery of Enceladus's ocean and plumes was one of Cassini's greatest achievements. Before Cassini, the idea that such a small moon could sustain liquid water seemed unlikely. Its size suggested it should have frozen solid long ago, but tidal heating, caused by Saturn's gravity flexing the moon's interior as it orbits, provides the energy to keep the ocean liquid and to drive the geysers. Enceladus orbits in resonance with other moons, including Dione, which helps sustain this tidal heating over long timescales. Enceladus is now considered one of the most promising places in the solar system to search for life. Unlike Europa, Jupiter's icy moon, whose ocean lies buried beneath tens of kilometers of ice, Enceladus offers its ocean material freely to space through its plumes. A spacecraft does not need to drill through ice. It can fly through the geysers and directly sample the water. Cassini did this, but it was not equipped with the specialized instruments needed to detect life. Future missions could carry more advanced tools designed to analyze the chemistry of the plumes in greater detail, searching for biosignatures such as complex organic molecules, isotopic ratios, or even microbial cells. The surface of Enceladus also tells a story of ongoing activity. The south polar terrain shows few craters, indicating it is geologically young. Heat measurements revealed that the tiger stripe fractures are warmer than their surroundings, with temperatures reaching -93 degrees Celsius, -135 degrees Fahrenheit, far warmer than the -200 degrees Celsius, -330 degrees Fahrenheit, typical of the rest of the surface. This relative warmth is another sign of active processes below. Models suggest that liquid water reservoirs lie directly beneath the tiger stripes, feeding the geysers. Enceladus challenges our assumptions about where life can exist. It is tiny, cold, and far from the sun, yet it harbors liquid water, organic molecules, and energy sources, all three key ingredients for habitability. On Earth, life thrives wherever those conditions are met, from deep oceans to boiling hot springs to frozen glaciers. If life exists beyond Earth, Enceladus is one of the likeliest places to find it. The implications go beyond Saturn. If a moon as small as Enceladus can maintain an ocean and hydrothermal activity, then oceans may be far more common in the universe than previously thought. Many icy bodies in the outer solar system, Europa, Ganymede, Callisto, Triton, Pluto, may harbor similar oceans. Enceladus serves as a reminder that habitable environments can exist in unexpected places, even on tiny icy moons orbiting distant planets. In summary, Enceladus is a world of contrasts, small yet dynamic, cold on the outside but warm within, isolated yet connected to Saturn's rings. Its geysers turned it from an obscure moon into a central target for astrobiology. Cassini showed us a glimpse of its potential, but much remains unknown. Future missions may one day return to Enceladus to taste its plumes with instruments designed to detect life, perhaps answering one of humanity's greatest questions. For now, Enceladus stands as one of the most compelling reminders that even the smallest worlds can hold the biggest surprises. While Titan and Enceladus dominate the spotlight for their atmospheres, oceans, and potential habitability, Saturn's other large moons are far from uninteresting. Each carries the scars of billions of years of history, offering insights into the processes that shape not only Saturn's system, but also the wider solar system. These moons may not gush plumes or host methane lakes, but their surfaces tell stories of impact, geology, and mystery. Rhea is Saturn's second largest moon, measuring 1,528 kilometers, 949 miles across. It is an icy world with a surface dominated by craters of all sizes. Rhea's density suggests it is made mostly of water ice, with a small amount of rocky material. One of its most distinctive features is the network of bright, wispy streaks that stretch across parts of its surface. When first observed by Voyager, these streaks were thought to be deposits of fresh material, but Cassini revealed that they are actually icy cliffs, long fractures where the surface has been pulled apart and refrozen. Rhea also holds the distinction of being the first moon found to possibly have a ring system of its own. Cassini detected charged particle patterns suggesting the presence of faint rings or debris clouds orbiting Rhea, though direct imaging did not confirm this conclusively. Even without rings, Rhea's heavily cratered and fractured surface makes it a classic example of an ancient icy world. Dione is slightly smaller than Rhea, at 1,123 kilometers, 698 miles in diameter, but geologically more varied. Like Rhea, Dione also has bright streaks of icy cliffs, nicknamed wispy terrain. These features are evidence of tectonic activity in the moon's past, when its icy crust cracked and shifted. Dione's leading hemisphere is heavily cratered, while the trailing side shows smoother plains, suggesting resurfacing events. Cassini also detected hints of a tenuous atmosphere around Dione, composed of oxygen ions. While extremely thin and unbreathable, this exosphere may be linked to interactions between the surface and Saturn's magnetosphere. There is also evidence that Dione, like Enceladus, might harbor a subsurface ocean, though if it exists, it is much less active. This possibility adds to the growing idea that subsurface oceans may be common among icy moons. Tethys, at 1,062 kilometers, 660 miles wide, is another mid-sized icy moon. Its most striking feature is Ithaca Chasma, a giant valley stretching 2,000 kilometers, 1,200 miles, across and up to 100 kilometers, 62 miles wide. This colossal canyon runs nearly 3/4 of the way around the moon and may have formed when Tethys's internal ocean froze and expanded, cracking the surface. Another dramatic landmark is the giant impact crater Odysseus, which is about 400 kilometers, 250 miles across, nearly 2/5 of the moon's diameter. Despite such scars, much of Tethys's surface is bright and reflective, indicating a surface of water ice. Tethys is also associated with two Trojan moons, Telesto and Calypso, which share its orbit but remain locked at stable points ahead of and behind it. These tiny companions demonstrate the complexity of orbital dynamics in Saturn's system. Iapetus is one of Saturn's strangest moons. At 1,471 kilometers, 914 miles, in diameter, it is the third largest moon in the system and is famous for its two-toned appearance. One hemisphere is bright and icy, reflecting sunlight like freshly fallen snow, while the other is dark, coated in material that absorbs most of the light. This stark contrast puzzled astronomers for centuries, but Cassini helped clarify the mystery. The dark material likely comes from the outer Phoebe ring, which coats Iapetus's leading hemisphere as it sweeps through space. Once deposited, the dark coating absorbs sunlight, warming the surface and causing underlying ice to sublimate away. This process reinforces the contrast, creating the dramatic yin-yang effect we see today. Iapetus also has one of the most unusual features in the solar system, an equatorial ridge that runs around much of the moon's middle, rising up to 20 kilometers, 12 miles high. It makes the moon resemble a walnut. The origin of the ridge is still debated. Some scientists think it may be the remnants of a collapsed ring system that once orbited Iapetus, while others suggest tectonic activity caused the crust to bulge upward. Whatever its cause, the ridge makes Iapetus unique, a world that stands apart even in Saturn's diverse family of moons. Mimas, the smallest of Saturn's major moons at 396 kilometers, 246 miles across, is best known for its resemblance to the Death Star from Star Wars. This likeness comes from the enormous Herschel crater, which spans about 1/3 of the moon's diameter. The impact that created it nearly destroyed Mimas, and the moon's fractured surface bears the scars of that event. Mimas is otherwise heavily cratered and appears geologically inactive, but its orbit has profound effects on Saturn's rings. A resonance with Mimas clears the Cassini division between the A and B rings, proving that even a small moon can leave a giant mark on the ring system. Intriguingly, some measurements from Cassini hinted that Mimas may wobble in a way suggesting the presence of a subsurface ocean. If confirmed, it would mean that even this seemingly inert moon could hide secrets beneath its icy crust. Together, Rhea, Dione, Tethys, Iapetus, and Mimas form a group of icy satellites that complement Titan and Enceladus. They may not have thick atmospheres or active geysers, but they hold records of ancient impacts, tectonic shifts, and surface-altering processes that stretch back billions of years. Each moon adds to the richness of Saturn's system, showing how a single planet can host an entire gallery of worlds, each with its own personality and mysteries. Beyond the large and mid-sized moons, Saturn is surrounded by a vast population of smaller satellites. Some are only a few kilometers across, barely large enough to be considered moons, while others reach several dozen kilometers in diameter. What makes many of these small moons remarkable is not their size, but their role in maintaining and shaping Saturn's iconic rings. They are called shepherd moons. And without them, Saturn's rings would look very different. Several of Saturn's shepherd moons orbit within or near the rings, using their gravity to confine and sculpt the delicate structures. Among the most famous is Pan, which orbits inside the Encke Gap in Saturn's A ring. Pan is about 35 kilometers, 22 miles wide, and has a distinctive appearance. It looks like a walnut or ravioli, thanks to an equatorial ridge formed by material it has collected from the rings. As it orbits, Pan clears a sharp-edged gap in the ring material, maintaining the Encke Gap structure. Another key shepherd is Daphnis, slightly smaller than Pan at around 8 kilometers, 5 miles across. Daphnis resides in the Keeler Gap, a narrow space near the outer edge of the A ring. Its gravity pulls on nearby ring particles, creating wave-like ripples that extend vertically above and below the ring plane. These waves were directly imaged by Cassini, providing dramatic proof of the shepherding effect. Daphnis's tiny size makes its influence even more impressive, showing how even the smallest bodies can control vast structures through gravity. Saturn's F ring is one of the most complex and dynamic parts of the system, and it owes much of its behavior to two shepherd moons, Prometheus and Pandora. Prometheus, about 86 kilometers, 53 miles across, orbits just inside the F ring, while Pandora, about 81 kilometers, 50 miles across, orbits just outside it. As they move along their paths, their gravity stretches, twists, and disturbs the ring, creating knots, clumps, and streamers of material. The result is a constantly changing structure with features that appear and disappear over the course of hours or days. Cassini's images of the F-ring showed this chaotic ballet in exquisite detail, confirming the moon's shepherding role. Another interesting small moon is Atlas, which orbits just outside the A-ring. Like Pan, Atlas has a ridge of material around its equator, giving it a flying, saucer-like appearance. This ridge likely formed as Atlas swept up fine particles from the ring edge. These unusual shapes are not common among moons and highlight how living so close to the rings gives rise to unique structures. Beyond the ring system, Saturn hosts a wide array of irregular small moons. Some of these are Trojan moons, tiny bodies that share orbits with larger moons. For example, Tethys is accompanied by Telesto and Calypso, while Dione is trailed by Helene and Polydeuces. These Trojan moons occupy stable points in the larger moon's orbits, demonstrating how complex gravitational relationships can be. Though small, many are under 30 kilometers, 19 miles across, these Trojans are fascinating examples of how Saturn's gravitational influence can lock bodies into long-term stability. Farther out, Saturn is home to dozens of irregular moons, captured objects that orbit at great distances, often on inclined or retrograde paths. Many of these are likely remnants of collisions or captured asteroids from the early solar system. They are generally small, irregularly shaped, and dark, composed of material that contrasts with the bright, icy moons closer in. While these distant irregular moons play less of a role in shaping the rings, they show that Saturn's gravitational reach extends far beyond its immediate neighborhood. Together, Saturn's small moons act as both caretakers and record keepers. The shepherds maintain the sharp edges and gaps of the rings, demonstrating how gravity sculpts structures on scales much larger than the moons themselves. The Trojans illustrate orbital stability in action, while the irregular outer moons record the history of captures and collisions in Saturn's past. Cassini's close-up images of these bodies revealed that even the smallest moons are not mere lumps of rock and ice, but dynamic players in a much larger system. Without these small moons, Saturn's rings would be diffuse, ragged, and much less striking. Instead, the system we see today, sharp divisions, narrow gaps, delicate braids, and constantly shifting features, exists because these tiny worlds act as custodians. They are reminders that in planetary science, even the smallest bodies can exert the largest influences. While Saturn's rings and inner moons capture much of the attention, the planet's gravitational domain stretches far beyond the bright system we can easily see. At greater distances, Saturn hosts a vast population of irregular moons, small, dark, and often lopsided bodies that do not share the neat orbits of Titan, Enceladus, or the shepherd moons. Instead, these irregular satellites follow tilted, eccentric, and sometimes retrograde paths, meaning they orbit Saturn in the opposite direction of the planet's rotation. To date, astronomers have identified dozens of irregular moons around Saturn, bringing the planet's total moon count to over 140. Many of these moons are only a few kilometers wide, and they are likely remnants of captured asteroids or Kuiper Belt objects. Unlike the icy, spherical inner moons that likely formed with Saturn from its disk of gas and dust, the irregular moons are thought to be later additions, bodies pulled in by Saturn's immense gravity during the chaotic early history of the solar system. The largest and most studied irregular moon is Phoebe, which measures about 213 kilometers, 132 miles, across. Phoebe orbits far beyond Titan at a distance of about 13 million kilometers, 8 million miles, from Saturn, compared to Titan's 1.2 million kilometers, 746,000 miles. Its orbit is retrograde and highly inclined, tilted by 175 degrees relative to Saturn's equator. This unusual orbit strongly suggests Phoebe was captured rather than formed in place. Supporting this, Phoebe's composition is darker and more primitive than Saturn's inner moons, resembling objects from the outer solar system. Cassini visited Phoebe during its approach to Saturn in 2004, providing detailed images and data. These revealed a heavily cratered surface covered in dark material, with some craters exposing brighter ice beneath. Spectroscopic studies showed that Phoebe contains carbon dioxide, water ice, and complex organic compounds, making it chemically distinct from Saturn's other moons. Phoebe is also the source of the Phoebe ring, a vast and faint ring that extends millions of kilometers around Saturn. Dust and debris ejected from Phoebe's surface gradually spread along its orbit, creating the largest ring in the solar system. This dust also explains Iapetus's two-toned appearance, as material from the Phoebe ring accumulates on its leading hemisphere. Beyond Phoebe, Saturn's irregular moons are divided into orbital families, groups that likely formed from the breakup of larger parent bodies. Collisions in Saturn's distant past could have shattered captured objects, leaving behind swarms of fragments that continue to orbit as smaller moons today. These families are named after mythological figures, such as the Norse group, which includes retrograde moons like Skadi and Surtur, the Inuit group with prograde moons such as Kiviuk and Igerak, and the Gallic group with members like Albiorix and Tarvos. Each group occupies a distinct orbital zone, offering evidence of common origins. The irregular moons are generally dark, with surfaces that reflect very little sunlight. They are irregularly shaped and heavily cratered, resembling asteroids rather than spherical worlds. Their distant and tilted orbits make them difficult to study, but what little we know suggests they preserve a record of the early solar system's violent and chaotic past. By capturing and holding onto these bodies, Saturn has essentially archived fragments of the outer solar system. The existence of irregular moons also highlights Saturn's immense gravitational influence. Capturing an object into orbit is not easy. An incoming asteroid or Kuiper Belt object must lose energy to avoid simply slingshotting past the planet. This could happen through collisions, close encounters with other moons, or interactions with the gas disk during Saturn's formation. Once captured, these bodies were shaped by billions of years of impacts and orbital perturbations, leaving behind the irregular collection we see today. Though small and distant, the irregular moons matter because they connect Saturn to the broader story of planetary formation. They show how giant planets swept up stray material, how collisions shaped the architecture of the solar system, and how even today, the outer solar system holds evidence of its turbulent origins. They also affect Saturn's environment in subtle ways, like Phoebe's role in supplying dark dust to Iapetus. Future missions are unlikely to target these tiny, distant moons directly, but studying them with powerful telescopes can provide valuable insights. Observations with instruments like the James Webb Space Telescope may reveal more about their compositions, while long-term surveys could discover even more members of Saturn's irregular families. Each new detection adds to our understanding of how complex and sprawling Saturn's moon system really is. In sum, the irregular moons are Saturn's outermost guardians, a population of dark, captured objects orbiting on strange and tilted paths. They are leftovers from an earlier era, preserved by Saturn's gravity. While they may not sparkle like the rings or dazzle with geysers like Enceladus, they expand Saturn's domain far into space, making its system one of the most diverse and extensive in the solar system. Saturn is not only massive and ringed, but also enveloped in an invisible yet powerful structure. Its magnetosphere, the region of space dominated by the planet's magnetic field. While Jupiter's magnetosphere is the largest and most intense in the solar system, Saturn's is still immense, extending hundreds of thousands of kilometers into space. The magnetosphere acts as a shield, protecting Saturn and its moons from charged particles streaming from the Sun, while also shaping the environment around the planet in striking ways. Saturn's magnetic field is generated, like Earth's, by a dynamo effect deep within the planet. Beneath the thick atmosphere of hydrogen and helium lies a layer of metallic hydrogen, a strange form of the element created by the planet's enormous pressure. In this metallic state, hydrogen conducts electricity, and the motion of the fluid layers inside Saturn generates a magnetic field. What makes Saturn unusual is that its magnetic field is nearly perfectly aligned with its rotation axis. For Earth, the magnetic axis is tilted about 11 degrees relative to the spin axis, while Jupiter's is tilted about 10 degrees. Saturn's tilt, however, is less than 1 degree, so aligned that for decades, scientists struggled to measure the length of Saturn's day using magnetic data. The magnetosphere extends outward to about 1.4 million kilometers, 870,000 miles, on the sun-facing side before being compressed by the solar wind, and much farther, tens of millions of kilometers, on the night side, where it forms a long magnetotail stretching away from the sun. Within this vast region, charged particles, mostly electrons and protons, are trapped and guided by Saturn's magnetic field lines. These particles originate both from the solar wind and from Saturn's own system, particularly from its moons. One of the biggest contributors to Saturn's magnetosphere is Enceladus. The plumes erupting from its south pole inject huge amounts of water vapor and ice grains into space. These particles become ionized and incorporated into the magnetosphere, creating a plasma environment rich in water group ions. This is different from Jupiter's magnetosphere, which is dominated by sulfur and oxygen ions from its volcanic moon Io. In effect, Saturn's magnetosphere carries the fingerprint of its icy moons. Saturn's magnetosphere produces auroras, similar to Earth's northern and southern lights. When charged particles spiral along magnetic field lines and crash into the upper atmosphere, they cause gases to glow. At Saturn, these auroras appear near the poles as shimmering ovals of ultraviolet light, sometimes visible in infrared or even in visible wavelengths. The Hubble Space Telescope and Cassini both observed Saturn's auroras, which change with the intensity of the solar wind and with conditions inside the magnetosphere. These light shows demonstrate the dynamic nature of Saturn's magnetic environment. The interaction between the magnetosphere and Saturn's rings is also significant. The rings are not simply passive structures of ice, they are electrically active. Ultraviolet radiation and energetic particles knock electrons off ring particles, creating charged surfaces that interact with Saturn's magnetic field. Cassini detected ring rain, streams of charged water molecules falling from the rings into Saturn's atmosphere along magnetic field lines. This process links the rings directly to Saturn's magnetosphere and even influences the chemistry of the upper atmosphere. Saturn's moons also feel the influence of the magnetosphere. For example, Titan orbits within its outer boundary, sometimes inside and sometimes outside of the magnetosphere, depending on solar wind conditions. When inside, Titan is shielded from direct solar wind bombardment, but its thick atmosphere still interacts strongly with Saturn's magnetic field, creating an induced magnetic environment. Dione and Rhea, too, show signs of magnetic interactions, with charged particles striking their surfaces and creating tenuous atmospheres of oxygen ions. Cassini made major contributions to our understanding of Saturn's magnetosphere. Its instruments mapped the structure of the magnetic field, measured plasma densities, and studied the behavior of charged particles. Among the surprises was how variable Saturn's magnetosphere is, responding not only to the solar wind, but also to internal dynamics, like the contributions of Enceladus's plumes. Another puzzle was Saturn's rotation period. Scientists expected to measure it from periodic variations in the magnetic field as they had done for Jupiter, but Saturn's near-perfect alignment meant that method failed. Instead, Cassini had to use periodic radio emissions to estimate the planet's day length, which turned out to be about 10 hours and 33 minutes, though even this measurement varied over time. Saturn's magnetosphere is less intense than Jupiter's, but that makes it more hospitable for spacecraft exploration. While Jupiter's radiation belts are so harsh they can destroy unshielded electronics, Saturn's radiation environment is milder, allowing Cassini to operate for more than a decade in orbit. This accessibility means Saturn is an excellent natural laboratory for studying how giant planets generate and sustain magnetospheres and how those magnetic environments interact with rings and moons. In the broader context of planetary science, Saturn's magnetosphere shows how diverse these magnetic environments can be. Earth's protects us from solar storms and cosmic rays. Jupiter's dominates an enormous region of space, and Saturn's creates a unique balance between planetary shielding and moon-driven plasma dynamics. Each one adds to our understanding of how planets interact with their space environments and how magnetic fields may shape conditions for habitability. In summary, Saturn's magnetosphere is a vast, invisible shield, intricately linked with its rings, moons, and atmosphere. It protects, shapes, and energizes the system, turning the space around Saturn into a dynamic, electrically charged environment. While we cannot see it directly, its effects are everywhere. In the shimmering auroras, in the structure of the rings, in the chemistry of the moons, and in the subtle signals detected by spacecraft. It is one more layer in Saturn's identity, a reminder that even beyond what our eyes can see, the planet commands an extraordinary realm of influence. Saturn has fascinated humans for millennia. Its striking appearance in the night sky with a golden hue and slow movement earned it a place in ancient mythologies across cultures. But for most of history, Saturn was simply a bright, wandering star to the naked eye. The true complexity of the planet, its rings, moons, atmosphere, and magnetosphere, only began to emerge in the last 4 centuries, as telescopes and spacecraft unlocked its secrets. The story of Saturn's exploration begins in 1610, when Galileo Galilei turned his telescope toward the planet. Through his small, imperfect instrument, he saw what looked like ears or handles sticking out from Saturn's sides. He could not resolve the rings clearly, so he assumed Saturn might be a triple planet, one large body flanked by 2 smaller ones. A few decades later, in 1655, the Dutch astronomer Christian Huygens, using a more advanced telescope, correctly identified the rings as a flat, thin disk surrounding the planet. Huygens also discovered Titan, Saturn's largest moon, marking one of the most significant discoveries in planetary astronomy. Over the next 2 centuries, other astronomers made key contributions. Giovanni Domenico Cassini discovered 4 more moons, Iapetus, Rhea, Tethys, and Dione, in the late 1600s. He also noted a dark gap within Saturn's rings, now called the Cassini division, which separates the A and B rings. These early observations laid the foundation for our modern understanding of Saturn as a complex planetary system rather than a single object. The modern era of Saturn exploration began with spacecraft. In 1979, Pioneer 11 became the first probe to fly past Saturn. It revealed new details about the planet's atmosphere, rings, and moons, and provided the first close-up images. Pioneer 11 also discovered 2 new moons and measured Saturn's magnetic field, but its instruments were limited, and the real breakthroughs came with the Voyager missions. Voyager 1 flew past Saturn in 1980, followed by Voyager 2 in 1981. These missions transformed our knowledge of the system. They sent back spectacular images of the rings, revealing intricate structures and braids, and discovered new moons such as Prometheus and Pandora. They provided close looks at Titan, though its thick atmosphere hid the surface from Voyager's cameras. The Voyagers also observed the bizarre 2-toned surface of Iapetus and the tortured terrains of Dione and Rhea. Together, The Voyager encounters turned Saturn from a distant gas giant into a richly detailed planetary system, filled with surprises. The greatest leap forward came with the Cassini-Huygens mission, a joint project between NASA, the European Space Agency ESA, and the Italian Space Agency ASI. Launched in 1997, Cassini arrived at Saturn in 2004 after a 7-year journey through the solar system. Once in orbit, it spent 13 years studying Saturn, its rings and its moons in unparalleled detail. Cassini carried 12 scientific instruments and dozens of cameras, while the attached Huygens probe was designed to land on Titan. In January 2005, the Huygens probe parachuted through Titan's atmosphere, becoming the first spacecraft to land on a moon of another planet. It returned images of river channels, pebbles of water ice, and a flat plain coated in methane-soaked material. This was humanity's first direct contact with Titan, and it revealed a world both familiar and alien. Meanwhile, Cassini orbited Saturn hundreds of times, executing close flybys of Titan, Enceladus, and other moons. It discovered geyser plumes erupting from Enceladus, proving the existence of a subsurface ocean. It mapped Titan's methane lakes and seas, observed seasonal changes in Saturn's atmosphere, and captured storms larger than Earth. Cassini also studied the rings in fine detail, identifying small moonlets, waves, and dynamic processes that constantly reshape them. Cassini's mission was extended multiple times as it continued to deliver groundbreaking discoveries. In its final phase, called the Grand Finale, Cassini performed a daring series of dives between Saturn and its innermost rings, gathering data from regions no spacecraft had ever visited. On September 15, 2017, Cassini ended its mission by plunging into Saturn's atmosphere, transmitting data until it was destroyed. This controlled end ensured that the spacecraft would not accidentally crash into and contaminate Enceladus or Titan, worlds that could harbor life. Through Cassini-Huygens, humanity gained not only data, but also a sense of Saturn's grandeur. The mission returned over 450,000 images, discovered new moons, and fundamentally reshaped our understanding of how gas giants and their systems work. It also raised new questions. Could life exist in Enceladus's ocean? What chemistry unfolds in Titan's atmosphere and seas? How long will Saturn's rings survive? Looking ahead, Saturn is not forgotten. The most exciting mission on the horizon is Dragonfly, NASA's rotorcraft lander set to explore Titan in the 2030s. Unlike Huygens, which stayed in one spot, Dragonfly will be able to fly from site to site, sampling different regions of Titan's surface. It will study the moon's chemistry, geology, and potential habitability in far greater detail. Future missions may also return to Enceladus to fly through its plumes again, this time with instruments capable of searching directly for signs of life. In a sense, our exploration of Saturn is still in its early stages. Telescopes gave us a glimpse, Pioneer and Voyager provided the first close-ups, and Cassini-Huygens turned Saturn into a fully realized world system. Future missions will push deeper, answering questions about habitability, chemistry, and the evolution of giant planets. Saturn's rings and moons continue to offer mysteries that demand investigation, ensuring that this distant giant will remain a focus of exploration for decades to come. Saturn has held a place in human imagination long before telescopes revealed its rings. To ancient observers, it was one of the 5 wandering stars that moved differently from the fixed background of stars. Because it was the slowest moving of them, completing its circuit of the sky roughly once every 29.5 years, Saturn became associated with time, age, and cycles of life. In Roman mythology, Saturn was the god of agriculture and time, a figure both creative and destructive, whose reign was linked with abundance, but also with inevitable decline. In India, Saturn is called Shani, a powerful influence in astrology, often seen as stern, but just. Across cultures, Saturn has been a symbol of patience, endurance, and sometimes fear, representing the limits of human life and effort. With the invention of the telescope, Saturn's cultural weight only grew. Galileo's sketches of its handles puzzled his contemporaries, while Huygens' revelation of the rings gave the planet a mystique unmatched by any other. The sheer beauty of Saturn's rings made it a favorite target for amateur astronomers, whose telescopes could reveal their delicate structure even centuries ago. Writers, artists, and philosophers were captivated by Saturn, seeing in it both beauty and strangeness. Its rings, unique among the planets, made it a natural symbol of mystery, complexity, and elegance. In literature and science fiction, Saturn and its moons have often been imagined as gateways to the unknown. In the 19th and 20th centuries, before spacecraft revealed their true nature, Titan and other moons were popular settings for speculative stories. Titan, with its thick atmosphere, was imagined as a place where life might exist, and this idea persists today with even stronger scientific backing. In film, Saturn often plays a supporting role as a backdrop for space exploration, its rings providing an iconic visual. Stanley Kubrick's 2001, A Space Odyssey was originally set to feature Saturn, though practical challenges in rendering the rings led the filmmakers to use Jupiter instead. Still, Saturn remains one of the most cinematic and recognizable planets in human culture. In astrology, Saturn continues to represent discipline, challenge, and long-term cycles. The so-called Saturn return, when the planet returns to the same place in the sky as it was at a person's birth, happens about every 29 years and is often seen as a time of reckoning or maturity. While astrology is not science, the persistence of Saturn's symbolic power shows how deeply it is woven into cultural thought. On the scientific front, Saturn remains a frontier of exploration. The Cassini-Huygens mission transformed our understanding, but it also left behind as many questions as answers. How long will Saturn's rings survive before they fall into the planet as ring rain? What chemical processes unfold in Titan's lakes and atmosphere? And could they represent a different kind of prebiotic chemistry than what occurred on Earth? Does Enceladus harbor life in its ocean, thriving around hydrothermal vents? Even smaller moons like Dione and Mimas may hold hidden oceans, challenging our assumptions about where habitable environments can exist. The next great mission on the horizon is Dragonfly, NASA's nuclear-powered rotorcraft lander designed to explore Titan. Launching in the mid-2030s, it will arrive in the 2040s and spend years flying from site to site across Titan's surface. Unlike past missions, Dragonfly will be mobile, capable of sampling dunes, frozen plains, and even the edges of methane lakes. Its goals are ambitious: to study Titan's complex chemistry, to look for prebiotic molecules, and to evaluate the potential for habitability. It may even answer whether Titan represents a kind of second Earth, where life could emerge under very different conditions. Enceladus is also a high-priority target for the future. Several mission concepts, such as Enceladus Orbilander, propose orbiting the Moon, flying repeatedly through its geysers, and eventually landing to study the icy surface. By directly sampling the plumes with life detection instruments, such a mission could determine whether Enceladus's ocean contains living organisms. This would be one of the most profound discoveries in human history. Beyond these targeted missions, Saturn continues to inspire questions about planetary systems more broadly. Gas giants like Saturn play a central role in shaping solar systems, influencing the formation of planets and distributing material. By studying Saturn, scientists gain insight into how giant planets function across the universe. With thousands of exoplanets now known, many of them gas giants, Saturn serves as a nearby example we can study in detail, helping us interpret what we see around other stars. Culturally, Saturn is likely to remain an enduring symbol of mystery and time. Its rings make it instantly recognizable, even to people who may not know much about astronomy. In art, literature, and science fiction, Saturn provides a canvas for exploring themes of beauty, impermanence, and the search for life beyond Earth. In science, it remains one of the most dynamic and compelling laboratories in the solar system, a place where the boundaries of habitability, chemistry, and planetary physics are tested. In conclusion, Saturn is more than a distant gas giant. It is a system of worlds, an engine of scientific discovery, and a cultural touchstone. From ancient myths to modern missions, it has challenged us to expand our understanding of the universe. As future spacecraft return to its moons and skies, Saturn will continue to reveal new surprises. Whether through methane seas on Titan, plumes on Enceladus, or the delicate dance of its rings, Saturn ensures that humanity's gaze will never stop turning toward the golden giant with wonder.